So hi, everyone. Thanks so much for joining. We're going to go ahead and get started. So today we're going to give a quick workshop on qualitative data analysis. We are the Statistical Consulting Lab here at ETSU. So we are in person in the lab in Gilbreth 308M, which is right over here in like that office space on the third floor of Gilbreth. We do have in-person hours. You can walk in if you'd like. We are open from 9 to 2 on Monday and Wednesday, and then 9 to 3 on Thursday, Tuesday, Thursday, I think, and Friday. You can always walk in, or you can send us an email at scl@etsu.edu. And so we'll go ahead and get started. Okay, so my name is Anna White, and all of us here are in the Applied Data Science Master's Program here at ETSU. And so
I'm Jonah Welch.
I'm Taylor Bowles.
So that's who we have with us today. And so real quick, what we're going to be discussing today, first, we're going to go over in general, what is qualitative data and how is it different from quantitative data. We're also going to talk about different descriptive statistics you can use, as well as visualizations. Then we're going to deep dive into proportion tests, what they are and how to do them, as well as the chi-square test of independence and what they are and how they do them, or how you can do them. And then we'll go on to some examples of, from beginning to end, how can you analyze some qualitative data. So what is qualitative data? So qualitative data, specifically when we use this term, we are talking about categorical data. And so this is going to be data like sex, race, so demographic information, as well as yes or no responses to survey questions, and as well as open-ended survey responses. And so qualitative data is going to look like this. So any multiple choice survey response is going to be qualitative data. So here is just an example. How many years of experience in retail do you have? Even though our responses technically are numbers, you have 0 to 1 years, 1 to 3, and 3+, it's still qualitative data, the data you will get out of asking people this question. So if you're doing a survey and you do want some type of quantitative answer from your survey question, if you ask that same question, but like this, with a blank to fill in where people could put, oh, I have 1.5 years. And then if you had enough data, then you could do some quantitative data analysis. But in general, survey responses are going to be qualitative. And that's really what we're going to focus on today. So next, descriptive statistics. You are very limited with descriptive statistics when it comes to analyzing qualitative data. And when I say that, I mean you can only really report counts and frequencies. And what's really important to remember here is that you cannot find the mean of qualitative data. And so what I mean is, if you ask a yes or no question and say, what's the mean response? That doesn't really make sense. You could say the majority of people said this, or this, 75% of people said yes, and 25% said no, but you can't really say the mean response. And if you can't take the mean of something, you certainly can't get standard deviation from that either. So just something to keep in mind if you only have purely qualitative data. So again, that same example, let's say that you surveyed 50 people. So how you could describe that data, a really good way to do that, and you'll see us do it a lot throughout this presentation, we're going to use tables. And so in this table, we have counts and frequencies. So we have our responses for our survey question. So looking at this, you can easily tell, oh, so you sampled in total 50 people and asked them this question, and 74% said they had 0 to 1 years of retail experience. So, and then let's look at this other example. Are you a student, yes or no? This could also easily be shown in a table. And so here, same thing, you sampled 50 people, asked them this question, and 54% said no, they were not a student. And so another great way to kind of describe and look at qualitative data, if suppose that you had asked those last two questions, so how many years of retail experience do you have, and what yes or no, are you a student? If you ask that in the same survey and you wanted to look at how these kind of two questions or responses interact, you could also do that. And we would call this a two-way table. And so here at a glance, you can see I surveyed 50 people. I asked them these two questions. It looks like 20 people that I surveyed were students who only had 0 to 1 years of retail experience. And so next we're going to talk about, so as you can tell, the descriptive statistics are very limited for purely qualitative data. Like I was saying earlier, and you are going to find, no surprise, no shocker, the same thing when you look at different types of data visualization techniques. So you can do a bar chart, a pie chart, stack bar graph, or stack bar chart, and a couple others, some kind of variants of this. So for that same years of experience question, you can easily show in a graph like this. This is going to be a bar chart, and you can do this in count or frequency. It's kind of up to you, but they kind of display the same thing. And just so you know, all the graphs used in this presentation, we make in Excel. So you do not need to know or have a lot of software experience in order to make something that can really at a glance communicate to people what your data looks like. And so also here's a pie chart. So yeah, at a glance, for those people who asked whether or not they were a student, you can clearly see 46% said yes, they were. And so something to keep in mind too, when you use pie charts, don't overdo it. People can tell when you overdo it. Just keep in mind that use them sparingly, and keep in mind that you're really when you're doing a pie chart, you're really showing parts of a whole, and make sure that there is a whole that your whole group of people that you are trying to describe using one. And so finally, here's an example of a stacked bar chart. And so just like that two-way table is going to convey that same type of information. So we have the different bars for years of experience, and then we have it color coded, yes or no, are you a student? And so we can kind of just show those splits, and you kind of see as you increase years of experience, it looks like more of those people are not students who are more experienced compared to those who are students. So next, Jonah's going to come and talk a little bit about proportion tests.
Yeah, so when using qualitative data, the proportion tests are used a lot. So what is a proportion test? A proportion test is used to analyze the proportions as well as the frequencies of the different categories within a qualitative variable. So the popular proportion tests include the chi-square test, the Fisher's exact test, the Yates correction, the McNamara's test, as well as the odds and risk ratios. And we'll go into a little bit more detail in each of these in later slides. So when to use a proportion test, the common scenarios in which to use a proportion test are comparing group proportions. Do the proportions differ across the multiple groups? The test and independence, are the variables independent of each other? Before and after comparisons, analyzing changes in the proportions over time, and the risk analysis, calculating the odds and risk of doing like a study, like medical studies. So the assumptions varied by test, but the majority of the assumptions are that you need categorical variables, a small sample size, independence between variables, and random or stratified random sampling. So now we're going to go into a little bit more detail about each of the different tests, the popular tests that I mentioned. So the Fisher's exact test is used with small data sets and test independence in those like two-way 2x2 tables. And the null hypothesis is that the variables are independent, and the alternative hypothesis or that they're dependent on each other. The McNamara's test tests the changes in the paired binary data, for example, like pre and post tests. So the null hypothesis is there's no difference. The alternative hypothesis is that there's a significance difference over time. So then the odds and risk ratios compares the odds and risk of an outcome between the two groups. For an example, the likelihood of developing a disease or condition or in the treatments going into them. And if the odds ratio or risk ratios don't equal 1 and the confidence interval does not even include 1, there is a significant association. So the chi-square test of independence, we'll go further into detail about this test in a later part of this presentation. And the Yates correction is a correction of this chi-square test of independence when used in 2v2 tables with small expected frequencies. The Yates correction is usually applied automatically when using like a statistical software like Python or something to run the chi-square test. And it's interpreted the exact same way as the chi-square test of independence. So for the next thing I will talk about is the one sample proportion test. This is like the simple proportion test when you know the outcomes. So the one sample proportion test is a test to determine if the outcome from the observed population is significantly different than the population's hypothesized or known outcome. If you know what it was supposed to be and it's different than the observed. So there's two different kinds. There's the two-tailed test and the one-tailed test. The alternative hypothesis for the two-tailed test is just that the two outcomes differ. However, for the one-tailed test, it's whether the observed population is greater than or less than the expected. And then the null hypothesis is no difference. So the test statistic for this one sample proportion test is the z-score, and it's calculated as the observed proportion minus the hypothesized or known proportion divided by the square root of the proposed hypothesized proportion times 1 minus the hypothesized proportion divided by n. So let's just say that according to a study, only 67% of people said that they're ready for the semester to end. But however, you were expecting that 3/4 of the population was going to say that they were ready for the semester to end. So for this example, let's just say that the sample size was 100 students to make things easier. So 75% is 0.75, so that's the null hypothesis, is that's what you were expecting it to be. The alternative hypothesis is that it was not 0.75. So you plug in the observed, the 0.67, and you plug in the 0.75 of the expected or known, and you plug that into the formula, and you get a result of the z-score being negative 1.85. Then you take this negative 1.85 z-score and you look at the z-table. We did not include a z-table today, but you can easily just search it up. And when you look up the p-value associated with the z-score of negative 1.85, the p-value is 0.0322. And since the p-value is less than the significant value of significance level of 0.05, you would reject the null and conclude that there is a significant difference between the observed results and the expected results.
Okay, so let's talk about the chi-square test of independence. When would you use the chi-square test of independence? So basically, you'll use that when, of course, you're looking at the possible relationship between two categorical variables, and in particular, to test whether the variables are independent of each other or dependent on each other. All right, so there are some assumptions that need to be met before going further with the chi-square test of independence. Of course, you want your variables to be categorical, independence of observations. You don't want one observation to somehow be able to affect another observation. Random sampling of the data, of course, and then often expected frequency counts. So usually it's around 5. It could differ depending on what you're looking at. All right, so here's just a general breakdown of the procedure that goes on behind the scenes when you're doing it. You have to look at your degrees of freedom. So to do that, you would look at how many rows you have in your data set, minus 1, and then you would multiply that value by the number of columns, minus 1. And then you usually have like a significance level, and often it's 0.05. So you would use that degrees of freedom that you found and that significance level, and you would look at a critical value table, and you can find those online. I linked one here, but you can just search it and see, and they're usually in the back of like stats books and different things. And so once you have those, you'll line up your degrees of freedom and your significance value, and you'll find the critical value. All right, so then after you do that, you have your observed values, and then you have your expected values. So you'll calculate your expected values, and you'll have that table. And then from those observed and expected values, you'll calculate your chi-squared value. So then once you have that chi-squared value, you'll compare it to the critical value that we found in the first step. And that will help you to determine if you need to accept or reject the null hypothesis. And I guess I should also mention, I didn't put this in here, but it's important. For the chi-squared test of independence, the null hypothesis is that they're independent of each other. And then the alternative hypothesis is that they're dependent on each other, so that there is a relationship. Okay, so I just wanted to go over a little quick example to try to help you all understand this. So here the question is the preferred pet food flavor dependent on the type of pet? And we'll use a 5% significance level. And so in this example, let's say that we want the count to be at least, or the frequency to be at least 3. So if you look at cat and chicken, it's 2. Cat and beef, it's 1. So what you can do to try to make that number greater is you can combine those two categories. So we went ahead and we combined the chicken and beef flavor, and then we left the tuna flavor by itself. So I'll just go ahead and say also, usually when you're trying to find the chi-squared test of independence value, there are online calculators and they're very simple to use. And you can even do it in statistical programs like R or even Excel. But I just want to walk through this one to kind of give you an idea of how you would do it by hand, what's going on. All right, so first, we'll try to look at the degrees of freedom. We have 2 rows, 2 columns in our combined table there. So 1 times 1 is our degree of freedom. And then I said we have a 5% significance level. So looking at the table, it's not here, but you can always look it up. I found that the critical value was 3.84. All right, so then you want to determine what are your expected values. So to do that, what you'll do is you'll take the row total, multiply it by the column total, and you'll divide it by the grand total. So let's see. Okay, so I'm going to write the formula here too for the chi-square test of independence. So it's the sum of the observed values minus the expected values squared by the expected value, or yeah, by the expected value, sorry. Okay, so thinking about the example that was on the previous slide, just for the first row and column, you had 3, and then you would subtract it by the expected value that we found. And then you would square that, and then you divide it by the expected value again. And then I'm just gonna erase this. Okay, so, and then you have to sum up all of those values that you find. So for this example, I went ahead and did it, and it's about 0.266. And think back to the critical value that we found, and that was 3.84. This chi-squared value is less than the critical value, so you would accept the null hypothesis. And in particular, you would say the preferred pet food flavor is independent of the type of pet. So, yes.
So next, we're just finally going to go over some of these examples that we created. And these are really trying to be a start to finish the whole procedure of how you could conduct a qualitative analysis depending on what kind of scenario and things that you were interested in. So in this scenario, suppose that we're interested in assessing the effectiveness of taking a personal finance class for students. And really we're interested in knowing whether or not those who have taken a personal finance class have better financial habits than those who have not. So suppose that you had 2 different groups of students, one who have taken a personal finance class and one who have not. And you ask them just the simple question, do you have a savings account, yes or no? And realistically, this is simplified for example's sake. You probably have to gather a bit more information to know whether or not the class is effective, but here we're going to say it's good enough. So, and then suppose this is what the data that you got looks like. So looking at these tables, you can see that we sampled 70 students who have taken a personal finance class. Well, then we sampled 87 students who have not taken a personal finance class. And of those who have taken a class, we found that about 63% of those students do have a savings account, as opposed to only about 46% of students who have not taken a personal finance class. So in order to answer this question, whether or not these proportion of students who have taken the class and who have not, whether or not they're a proportion of those students who have taken the class, it differs significantly whether or not they have a savings account. We would actually do a 2-sample proportion test, so kind of like the test that Jonah showed earlier, but a little bit more in depth. And so like we were saying earlier, and if you've ever had a lot of experience doing any kind of statistical analysis, we always have assumptions because there's always caveats whether or not things are appropriate. So we got to check some stuff out first. So the first is, was this a random sample? In most cases, we're just going to go ahead and assume yes. For your own case, it does depend on how you select people who you give your survey to, but we're going to assume yes, it was a random sample. And so next we need to know, are the two samples that we took, those students who have taken class and those who have not, are they independent of one another? And really what we mean here is we need these two groups to be mutually exclusive. So one person can't be in both groups. And yeah, you can't have taken a class and also simultaneously have not taken a class at the same time. So these two groups are independent of each other, which is good. And then another assumption we have is within each sample, so within those students who have or have not taken a class, are those individuals independent of one another? And yes, they are. Assume yes, yes, they are. So, and then finally, the last one, the fun one, we need to know whether or not of our two samples, if they are considered large enough to be sufficiently large and approximately normal, which is very important in statistics. And this assumption really is going to determine whether or not we can say our results are reliable. So it is important that we check it. And so here's the formula. So N1 is going to be the sample size in our first group that we sampled, and then P1 is going to be the proportion of yeses in that sample. So we multiply these two numbers together, and we need them to be greater than or equal to 5, while conversely, but at the same time, we need that same sample size multiplied by 1 minus P1, which in this case is going to be the portion, 1 minus P1 is just the portion people who said no in this case. And so we need to we multiply that by the sample size is also greater than or equal to 5. And so for our first sample, so for our first group, those who have taken a personal finance class, using the data that we collected with a sample size of 70, we find that yes, both of these numbers, and then we multiply it out, are greater than or equal to 5, so that sample is sufficiently large. Yay, great. And so then we have to do it again, same exact procedure, where we're just going to use the information from our second sample, which were students who have not taken a personal finance class. And doing this multiplication, yes, same thing. We find that both of these numbers are greater than or equal to 5, so yay, we can move on and conduct our analysis. And so again, it is statistics, so you do need to know what the null and alternative hypothesis are for your test. And so the null is, we're going to assume that the two population proportions are equal, while the alternative is going to say no, they are not equal. And so our significance level is going to be the standard 0.05 in this case. And so next we need to find our test statistics. So you can definitely see a pattern. The way that we conduct this is very similar to the way Jonah did his one sample, and even the way that the kind of squared procedure works. So anyway, we're going to have the test statistic. It's going to be Z because it's going to be based off the normal distribution. And so then we have P1 hat, that is just going to be from your sample, so the proportion of yeses in your first sample minus the proportion of yeses in your second sample. And here inside of the square root, this is called the pooled variance. And this really just comes from the fact that in our null hypothesis, we're going to assume that the two population proportions are equal. So we're going to find our test statistic assuming that they are equal. And so here we just have P hat, but it doesn't say 1 or 2. And this is going to be what we call our shared proportion. And how we find the shared proportion, the formula is over here. And so that's going to be X1, which is going to be not the proportion, it's going to be the number of yeses in your first sample plus the number of yeses in your second sample over the sample size for both of your samples. And so doing that, we find our shared proportion to be 0.535. And then using that in our formula and plugging in everything else, we were able to find our test statistic, which is 21.125. So really, in order to conduct a proportion test, you just need to know your sample size and then the proportion of yeses or nos, depending on your responses. So it is pretty simple procedure and not a lot of things that you need to know, but you can still conduct an analysis and get some answers to some questions that you're interested in. And so doing this, we need to find our critical value, which in this case, it's a 2-sample test based off just a normal distribution. So it's 1.96. And so, or you can find also at the same time the p-value using our test statistic of 21.125. That's pretty large. So our p-value is going to be approximately 0, which is certainly less than 0.05. And so from this analysis, we're able to conclude that we should reject the null in this case. And we conclude that there is a significant difference in the proportion of students with a savings account between students who have taken a personal finance class and those who have not.
Okay, so for our next scenario, we're going to imagine that we had a study conducted of 1,000 women where they investigated whether those who have a family history of breast cancer are have a greater risk of developing it. So let's just say of the 1,000 women, there's 500 women who have family history of breast cancer and 500 women who did not have a family history of breast cancer. So of the 500 women that do have the family history, 100 of them developed breast cancer, while 400 of them did not develop breast cancer. While with the no family history of it, only 50 developed breast cancer and 450 did not. So to address this scenario, we're going to use the odd and risk ratios. The odds ratio compares the odds of the event occurring in one group to the odds of the other, and the risk ratio compares the probability of an event occurring between the two groups and is calculated as the ratio of the probability or the risk of the event in one group compared to the probability in the other. So for the odds ratio, so the odds of developing breast cancer in women that have a family history of it, you take the 100 women who developed the breast cancer and divide it by the 400 women who had the family history but did not develop breast cancer, and you get 0.25 or 25%. So then for the odds of developing breast cancer with no family history of it, you get the 50 women who do not have a family history but did develop it, and divide it by the 450 of the women who had the no family history but did did not develop it, and you get 0.111. So then you take the 25 for 0.25 divided by the 0.111 and get 2.25. And you would interpret this as that means the odds of developing breast cancer are about 2.25 times higher for women with a family history compared to those who do not have a family history of it. So for the risk ratio, you do around about the same thing, but you do different numbers. So the probability of developing breast cancer for women with a family history of it, you take the 100 women who developed it, and then you have divided by the 500 total women who have the family history of it, and you get 0.2. So then for the probability of developing the breast cancer in women who without the family history, you take the 50 women who developed breast cancer but did not have the family history of it and divide it by the 500 total women who did not have a family history of it, and you get 0.1. Then you take the 0.2, divide by the 0.1, you get 2. And you would interpret this as this means that women with a family history of breast cancer are twice as likely to develop it compared to women who do not have a family history of it. If you have a certain thing that you're trying to test, you can build up upon it with confidence intervals and hypothesis tests, but to keep it short and just like concise and simple, we didn't dig into that.
Okay, so let's go over another example of the chi-square test of independence. And for this one, let's say you'll ask, what is your gender identity? To simplify it, just say male or female. And then we'll ask, what is or are your favorite animals? So for this one, the way that it's different is you could choose cat, you could choose worm, or you could choose cat or worm. So if the person were to choose both cat and worm, the categories would not be mutually exclusive. So how do we deal with that? And let's just say for this, no one chose neither. Someone chose at least something, or everyone chose at least one of those columns. Okay, so in order to do that, what you have to do is you have to break it down to cat only, worm only, and then to deal with the issue of mutual exclusion, we'll create a category that is for cat and worm. And for this one, we'll also use the 5% significance level. And to simplify things, I won't go through the whole process like I did before. I'll just include a screenshot of an online calculator that I use, because to be honest, that's probably what a lot of people will be using. Okay, so with this one, the online calculator, it has the chi-square statistic, but I don't have the value from a table to compare it to. So we'll look at the p-value here, and it does the same thing. So you can see that the p-value is, it's greater than 0.05. So you would conclude that, that the preferred pet is independent of the gender of a person. So you would accept the null hypothesis, independence. And
So thank you. That's all we had planned for today. I hope that kind of cleared up and gave you a good overview what your options are if you have just qualitative data. Of course, if you had some quantitative data, you would definitely have some more questions that you could answer and some more direction you can go in. But thank you so much. We have one workshop scheduled for the rest of the semester. It's next week, next Tuesday in this room or online from 3:30 to 4:30, and it's going to be an introduction to SAS. We're gonna talk about importing data, the basics of SAS syntax, as well as how to do some descriptive statistics and data visualizations. I believe we're also gonna go over how to do ANOVA and multiple linear regression. So that will be good. And then, thank you. We'll stay on for some questions. And we do have this QR code. If you would like to give us some feedback about how we did, also make suggestions on future workshops, feel free to do so. Always optional though. We appreciate the feedback. And thanks.